So in this video, I wanted to go over the solution of problem 5.36 from the practice exam. We have a beam which is subjected to a distributed load. We'll notice that the density tapers up linearly from 0 at point C to a maximum value of 600 newtons per meter. And this beam is supported by two spring supports attached to both point C and point D. And what we're told is if we know the stiffness or the spring constants for both of those springs, can we determine how much the beam actually tilts when the load is applied? And I should have added in addition that we're told that the springs rather, are unstretched when there's no load applied on the beam. So when you think about solving this problem, like all problems in statics, we kind of tell ourselves that we need to move towards drawing a free body diagram. And one thing we know is that the reactions associated with these springs are going to be directed along the direction of the spring. We don't know their magnitude, of course, but we can solve for their magnitude using a free body diagram if we replace the distributed load by a single equivalent point load. And the reason that we can do that is, of course, this will be a statically determinate problem. In fact, it's going to be very easy to solve. Namely, if we have those two unknown forces associated with the reactions, we actually can write three equations of equilibrium, and we'll only need to write two equilibrium equations related to rotation actually applied at points C and D, as we'll see here in a minute. But how do we actually start by replacing this distributed load by a single equivalent load? Well, remember that if we're going to replace it by a single equivalent load, we need to know two things. We need to know the magnitude of that single equivalent force, and we need to know the point at which we'll apply it. Remember that if we know the density function, the way that we get the magnitude is just to integrate that entire density function over its span. And here, this linear density function is applied from measuring kind of an x-axis along the beam and defining point C as x equals 0. It's defined from x equals 0 to 3, and it just tapers up in a linear fashion. So what I need to do is integrate this density function from x equals 0 to x equals 3, and that density function is just going to be a simple linear taper. However, I don't have to integrate this at all. Eventually, moving into the next few chapters when we compute centroids, we will compute a lot of integrals by hand. But here, remember that the definition of the definite integral is just the area under this curve. And this density function just traces out a triangular curve. And the area of a triangle is simply 1/2 the base times the height. So that's where I'm getting these numbers here. The 1/2 times the base, 3 meters, times the height, 600 newtons per meter. Of course, when I multiply something in meters by something in newtons per meter, the result will be in newtons. But this is just a formula for the area of a triangle. And what that's allowing me to do is integrate my density function and find the magnitude of my equivalent single force. The next thing that I need to do is determine where I would actually apply this force, at what distance along the beam. And if you remember back to when we originally introduced the concept of distributive forces, we said that we would apply them at the centroid of the area that's kind of traced out by the density function. And for the case of a triangle, you can do a table lookup, or you might remember, since we've dealt with this one a couple times, that it's simply going to be 1/3 away from the fatter portion of the triangle along the base. So since this triangle is 3 meters wide, 1/3 away from the fatter portion, which is on the right side, is going to be just b over 3 here. So if b is 3, that will be just 1. So it's going to be 1 meter to the left from the middle. Another way to say that is it's going to be 2 meters to the right from point C. So if you have any questions of how I determine that, feel free to let me know. Again, at this point, that's just something that you look up from a table, since we haven't talked about how to integrate in order to compute the centroid. So once I've replaced this distributed load by a single equivalent force, the free body diagram is going to look pretty simple. I'm just going to have my reactions associated with the spring at point C and point D, and I'm going to have that single equivalent load, which has a magnitude of 900 newtons, and it's applied at 2 meters to the right of point C. So how can I solve for, well, first and foremost, one thing that I should have said, if you notice in that problem description, it makes mention of the fact that this is actually going to tilt somewhat. And if you actually look at this, assuming that if we were ignoring the stiffness of the springs for now and just assume they're relatively close to one another, since that load is kind of distributed to the left side of the beam, one might argue or might think that side C is going to depress a little bit relative to side D, and it's actually going to tilt at kind of that kind of angle. And in order to draw your free body diagram, really you have to consider that in, because remember that that distributed load is always going to be normal to the beam, even if the beam tilts a little bit. So that's what I'm trying to show you here. Here's if the beam weren't tilting at all, drawn in the purely horizontal direction. And here's if it were to be drawn at an angle. So kind of the geometry of all of those forces is going to shift somewhat if there's a little bit of a tilt. Of course, the two springs, by definition, those reactions have to go along the dimension of the spring. So if one side tilts more relative to the other, they're still going to be straight up. However, this force associated with the distributed load will be slightly angled. So when I compute my moments, which I'm going to do in order to solve for these reactions, the distances will be a bit changed if there's a little bit of a tilt. So under the assumption that the tilt is very, very small, I can actually compute the moment about point C and point D. And what that will allow me to do is to get an equation that involves each of the reactions that I want to solve for by itself. So if I sum all moments about point C, remember that what we're going to do there is we're going to pin the beam at point C. Notice that the 900 Newton force is actually going to cause a clockwise rotation, kind of taking a scalar approach to computing the moment of this 900 Newton force. In order to do that in 2 dimensions, I need the direction of the rotation it causes. So that's a clockwise rotation, so it will be negative. I need the magnitude of the force. That's going to be 900 newtons. And I need the perpendicular distance. And in this case, for a purely vertical force, the perpendicular distance will just be this 2 meters. So that's where each of those 3 numbers comes from. In contrast, that tendency of the 900 Newton force to kind of swing the beam in the clockwise direction is going to be counterbalanced by the tendency of the reaction at D to pull it back in the counterclockwise direction. And if you think about it, since this reaction at D is so far away from point C relative to the 900 Newton force, it makes sense that FD is not going to have to be as strong of a force in order to counterbalance that rotation. That's just the way that torques work. And that's exactly what we see here. So we notice that the rotation associated with FD is in the counterclockwise direction, so it gets a positive term. We don't know the magnitude. However, we do know that the perpendicular distance is 6 meters. So if we solve this single equation for the single unknown FD, what we find is that FD is 300 newtons. So just like we expected, it's going to be a very small fraction of the 900 Newton force, because in terms of counterbalancing the rotation, this 900 Newton force is so close to point C that it has a very small lever arm relative to FD. In fact, it has a third of the lever arm, so it needs 3 times the force, which is why you have this 900 to 300 Newton relationship. Do the same thing to find the reaction at C, sum all the moments about point D. Notice if you're pinning at point D, in that case, the 900 Newton force will cause a counterclockwise rotation, so it gets the positive sign. It is at a perpendicular distance. Well, remember, if the whole beam is 6 meters, and this is 2 to the right, this remaining distance is 4 meters. That is counterbalanced by the tendency of FC, that reaction, to rotate back in the clockwise direction, so it gets a negative. And it wouldn't really matter if you switch your 2 signs around. It's just that for my counterclockwise positive convention, these are the signs that are assigned. But the key point is that they're of opposite signs because they're kind of counterbalancing one another. So if you go ahead and solve for FC, what you'll find is that FC is 600 newtons. So what that's going to allow us to do, these are just simply the forces that each of these springs are applying in order to lift that beam back up. So remember, for a spring by Hooke's law, if I know kind of the restoring force that's being applied by the spring, and I know the spring stiffness, which I was given originally, I can actually calculate the displacement that was necessary in order to create that restoring force. So what do I mean by that? Well, if the spring, for example, at C, ends up having to pull 600 newtons up, and I know how stiff the spring is, which I was given up here at the beginning. Now, if you notice, I'm defining the reaction forces by the point at which they're applied. They're actually defining the spring constants by the point at which they're attached. So force C is actually associated with spring that's attached to A or Ka. So if I know the stiffness and I know how much restoring force is being applied, I can compute what the actual displacement of that spring was. And that's all that is going on here. If you multiply the K's to the other side, you see that this is simply just an example of Hooke's law. In order to generate that restoring force, there must have been a marginal displacement of YC and YD. If you solve for both of those, what you find, and you can't kind of do it on a one-to-one basis because the springs have different stiffnesses. In fact, if you look, the spring that is attached at point B is actually a much stronger spring. So for a given amount of force, it's going to displace less. So this thing is going to be relatively substantially tilted when you actually solve for these 2 relative displacements, because this force that's being applied at D, not only is it a smaller force because of the location of this distributed load, but that spring is also stiffer. So that spring is also stiffer. So what that means is that displacement is going to be relatively small relative to the displacement at point C. In fact, it looks like it's about a factor of 4. So if we know that that entire beam, the right side depresses by 12.5 centimeters, and the left side in total depresses by 46.15 centimeters, we can find the little bit of tilt. So remember, if the whole thing goes down by 12.5, the actual quantity that you use in the tilt is 4.6.15 minus 12.5. So that's why this quantity in the numerator is the difference in those 2 things. And we can just use trigonometry because we know the beam is 6 meters in length total. And if you do that correctly, you should find that the actual tilt of that beam is about 3.22 degrees. So hopefully everyone, I think the 7 of you that ended up taking the practice exam all got that problem right. And that's definitely a good thing. Hopefully, those of you that didn't get a chance to attempt the practice exam, take a look at this problem before you take the exam.